In this video, we'll be deriving the well-known formula for finding the gravitational potential energy that is far more general than the more basic MGH, which only describes a change in GPE and really only works at relatively short heights. This more general formula can be used at basically any distance and gives a total value, not just a change in GPE. So how do we know it's true? And consequently, how do we derive it? If you're familiar with some very basic integral calculus, then the proof I'm about to show you, mathematically speaking, will be very straightforward. However, the concepts are perhaps more difficult to truly internalize. So I'm going to start by defining gravitational potential energy in a way that maybe reveals why calculus is needed to rigorously prove the expression we're going to develop together. The gravitational potential energy of two bodies is the work done by some external force in bringing the bodies from when they were infinitely far apart to where they are now. Notice that we're talking about both bodies, but that questions often seem to ask about the GPE of one body. So when you're asked about the gravitational potential energy of just one of those masses, that isn't technically correct. I wouldn't write that on a test, but just keep it in mind. I also want you to think about how we're imagining the object was brought in from infinitely far away. This process would have to have been done at some very low velocity in order to keep the kinetic energy low. Alright, so let me repeat that definition before we get started, because I will rely on it heavily when deciding the mathematics I'm going to do. The gravitational potential energy of two bodies is the work done by some external force in bringing the bodies from infinitely far apart to where they are now. So, let's get started. We know that we're looking for some work, and that work is force times distance. However, crucially, a major characteristic of gravity is the force is constantly changing as the distance changes, as can be seen by the fact that the force is dependent on the distance r. In fact, it's dependent on the inverse square of r. Nevertheless, our simple equation for work provides an important insight. All we're doing is finding the area underneath a curve whose axes plot force and distance. It just so happens that the force is constant, and so we can just use the formula for the area of a rectangle. So, we've learned that the integral of force with respect to distance is work. That is why we need to integrate our equation for gravitational force, which you should hopefully know is big G big M times m over r squared with respect to r, from infinity, as can be seen in the definition, to r. I want you to remember that this is the same principle as doing force times distance, as all you're doing is just finding the area underneath a curve. It just so happens that the force isn't constant. Alright, in any case, let's evaluate this integral. All this stuff up here in the numerator is just a constant, and dividing by r squared just means multiplying by r to the negative 2. So just raise the power by 1 and divide by the new power, and the integral is equal to negative gm times m times r to the negative 1. This is just equal to negative big G big M times m over r evaluated at r, subtracted from negative big G big M little m over r evaluated at r equals infinity. When r tends to infinity, this expression tends to 0, so we're left with the equation for work being negative big G big M little m over r. As this was the work done by our external agent, we know that this is equivalent to the gravitational potential energies of our bodies. Thank you for watching. This was a quick summary of the definition of gravitational potential energy and its derivation using calculus. I hope you found it helpful, and we'll check out some of my other derivations for common results in physics or some applications of what you just learned in my videos on orbital mechanics and escape velocity. Thank you for watching. Bye-bye.